So as introduced, I'm Jacopo Corbetta. I'm here to present this work in which we leverage the different views of the web to analyze and detect malware. So our work starts from a very simple observation. So any web page on the internet, like this HTML page that we have here, is consumed by two very different types of consumers. And one type of consumers are humans that visit these web pages through a web browser. And we have an example here of a web browser that has parsed this HTML page, fetched all the dependencies, images included, has built the layout of the page using cascading style sheets and so on and so forth, and is currently executing JavaScript so that the user is free to focus on how the page appears and interact with it. On the other hand, we have computer programs such as search engines or malware analyzers that are typically going to scan this page to extract some sort of information. And these programs are not necessarily willing to fully emulate a web browser, for instance, because they will not have the full timing necessary to do so, or because they don't have the computational resources to do it. And they will typically focus on exactly this type of information that they need. For instance, a search engine may focus on the HTML tree and specifically what links are present on the page or what keywords are present in the text and so on and so forth. So as we have seen, we have these two different actors, agents, so to speak, that are consuming the web, and they can have a different understanding of what a page means and what a page is supposed to mean to a user and to the program. And so what is the risk that arises from this? Is that a cybercriminal could create a web page that makes malicious content visible only to the human, but not to the program. So for instance, the malware analyzer would not see the malicious content, whereas the human that sees the page would actually see it. Or on the other hand, you could have all the data available to the program, but it's just the appearance of the page that is malicious and that fools the user. So again, the difference in these views can be a source of maliciousness and possibly to hide from large-scale crawlers or large-scale malware analyzers that typically do not run JavaScript, for instance, or do not download images. So in this work, we introduced two heuristics that try to explore or start exploring this problem and start to see if this difference in the views can be useful. Does it happen for malicious web pages? Does it happen for benign web pages? Could we use it to detect malicious web pages? And so moving on to our first heuristic, we focused on content that is easily seen by a human, but hard to get without simulating a full web browser. And in particular, we have started from a very simple observation that on the web, there is encapsulation and encoding, but the text payload is almost always transferred as is. So what do I mean exactly by this? So if we have a banking website, for instance, it's typical that the page is transferred to HTTPS, for instance, and it's typically encoded in UTF-8, and it's possibly compressed via gzip transparently by the browser. But once the HTTP payload is decoded correctly by the browser, we reach a well-defined payload that typically contains the text as is, typically simply in the in text nodes in the HTML document, for instance. So obviously, there's nothing that forces this to happen, right? I mean, you could create, you could mangle the text that you get from Ajax, or even from the HTML page. You could mangle it via JavaScript and completely modify it and start from a certain text and end with a completely different one. But there's very little reason to do this for a benign author, and there are a few fundamental reasons for this. First of all, one might think, well, maybe I can compress the text. I want my site to be as fast as possible, so maybe I will transfer text in a compressed form, and then I will decompress it on the fly in the web browser. But unfortunately, or luckily, at the typical sizes that we see in web pages, it's very hard to beat the built-in gzip compression that browsers and HTTP itself provides. And in fact, as an example, the commonly used minimizers do not significantly alter string literals. Also, many of the popular formats like XML or JSON are fully text-based and again do not alter the string literals. And in general, there is a preference in the web for the tools that are available and so on and so forth to use protocols that are in clear text and easy to debug. In fact, HTTP itself is an example of this. So based on this intuition, we have devised a heuristic that detects textual content that cannot be recovered without full JavaScript execution. So again, what is the motivation for this heuristic? A static analyzer will typically want to analyze the text or the content of the page as fast as possible, and a static analysis is typically a function of the size of the page, roughly. Whereas if you start executing JavaScript, then you have unpredictable delays, and you have to keep the entire page in memory at all times, because JavaScript could potentially alter the page completely and go from white to black and everything. So our heuristic is that spiders and static signature analyzers may not emulate the full web browser, and in particular may not execute JavaScript. So how can we detect if there is an obfuscation going on? What we look at is we start from an instrumented Firefox web browser, and we use it to visit a web page. And then we see what is the HTTP payload, what are the HTTP payloads after decoding, after decompressing, after stripping out HTTPS, for instance. What do they contain? What text do they contain? And then again, after we execute the JavaScript in the page, what text can we recover from the DOM tree, so from the page that the user will actually see? And then we compare these two text sources, and we try to see if there was obfuscation going on. And this is a little example that we have here. A text in the HTTP payload was presented in this obfuscated string. This is, in particular, this is base64 encoded. Then JavaScript was executed. It base64 decoded it, got to the text obfuscated content, and then this text can be freely added to the web page. For instance, by creating a new text element or by modifying an existing one, and so on and so forth. Now, our detector is relatively independent of what type of JavaScript is executed, so how exactly this text is decoded, quote unquote. But to give you a few examples, many of the ones that we encountered in our dataset didn't really go beyond doing simple unescaping or base64 decoding. But obviously you have the full power of JavaScript at your disposal, and JavaScript is a Turing-complete language. So in fact, a couple of weeks ago, Symantec reported on a phishing page sample that was transferring the text AS encrypted and decrypting it on the fly in JavaScript. So obviously the key was embedded in the web page. So again, nothing out of this world, but as we can see, this procedure of going from the HTTP payloads to the text in the DOM tree can be extremely complicated and can be very hard to emulate without actually executing the JavaScript. So here is how our detector works in particular. We start from the text in the web page, and we try to seek a justification for each of the words that is present. And what do I mean? I mean that for every word, we check that it has to be in one of the preceding HTTP responses, or in one of the URLs, or in one of the headers, or in one of the AJAX requests, and so on and so forth, but only the ones that precede the appearance of the word. And we also anticipate some common benign string operations that are performed in JavaScript, like concatenation and truncation. As an example, truncation sometimes happens when you have a large bit of text that is presented to the user, and the user is actually just presented with a row or two, and a button that shows show detail is presented. Sometimes the last word, for instance, is truncated. This is a classic example. And then again, we whitelist a list of strings that you can get directly from the JavaScript interpreter, such as the name of the months or the name of the days. Element names, these sometimes show up if error messages are printed on the page, and so on and so forth. And this is, so after building this detector, we try to see, where it triggers, how it triggers, what type of pages trigger this detector. And in particular, we tested it on a data set of about 150,000 pages. And we have two main sources for this data set. One is about 80,000 and are the most popular pages in the Alexa ranking. And this is, relatively speaking, a baseline of mostly benign web pages. And then we used Whipawet as another source of URLs and web pages. Whipawet is freely available analysis service that is provided by UCSB, and anyone can submit a URL, and WebOwet will try to analyze it, try to deobfuscate it, and see if the web page is malicious or not. And I should precise that we do not use the results of the WebOwet analysis in our work. We simply use WebOwet as a source of pages to analyze, live web pages to analyze. In particular, we have two sources from WebOwet. One is from past submissions and are filtered in the URL so that they contain with good likelihood fake antivirus web pages, so we can test our work on this particular type of scam. So just as an example, the keywords that we look for in the web page or in the URL, sorry, are about scan or virus and so on and so forth. So again, these pages are not all malicious. They are not, there is in fact a high amount of benign in this, but they have a good likelihood of containing fake antivirus pages. And then we use 50,000 live URLs as they are submitted to WebOwet with no particular filtering. And this is going to be the basis of our final evaluation. So again, WebOwet has various sources that include some benign ones. And in particular, we can expect from a relatively random sampling of pages, there is a large amount of benign ones, about 94%. And then we have several common scans. For instance, pharmacy scams are relatively common in this data set. And there's also a certain amount of pages generated by exploit kit, like Black Hole, that were trying to exploit the browser. And this is what our content obfuscation detector, how it triggered. We evaluated, in what we found, we evaluated if there were false positives or false negatives, in particular, as far as the content obfuscation is detected. So there were very few false positives, so very few cases where we thought there was content obfuscation, but there was actually none. And this is essentially because it's not particularly easy to parse the network payloads exactly as the browser does, especially because there's, for instance, the content encoding such as UTF-8 or other character set encodings and can sometimes be inherited by the HTML page. There are several heuristics that are also used by browsers. So this was a source of false positives, or if you will, an imperfection in our heuristic. We didn't find any false negatives in the about 3,000 samples that we manually examined to verify what negatives we could have missed. And these are the types of pages that our detector flagged. Obviously, in the Alexa source, we mainly detected benign web pages, about 52. In fact, exactly 52. And then we have, in the fake antivirus feed and in live submission, we have about 200 genuinely malicious web pages detected. So again, this is not exactly a perfect detection of malicious web pages. We have a relatively high number of benign web pages. But what is interesting is that it does automatically, fully automatically find content that the author wanted to hide. So content that the page author didn't want a static analyzer to see. So in a sense, we can say that content obfuscation is actually used by malicious and sometimes even by benign page authors, exactly to escape the detection of malware analyzers, sometimes even to escape the indexing by search engines. So in particular, several of the malicious pages that we found were not detected as such by WebOwet, because WebOwet mainly targets browser-based exploits, or if it has signatures for specific scams, it detects them. And on the other hand, we have a completely agnostic type of detection that also found several pure scam web pages that are just targeting the user instead of the browser. In fact, since our engine is completely independent from WebOwet, we also had this relatively interesting result. We found web pages that were detected by our heuristic, and when we looked manually at them, we said, well, these pages look very likely malicious. They, in fact, look quite complicated, possibly generated by an exploit kit. But WebOwet was marking them as benign, so we contacted the WebOwet maintainers and asked, what is going on? What are these pages doing? Are they really benign? And in fact, we found that these web pages were actually fingerprinting the JavaScript engine used by WebOwet and hiding from them. So just as an example of how completely independent our two engines were. So to proceed forward, we can refine our results, and we can do this by exploiting the fact that most of the scams that we saw in our dataset are realized as campaigns, so there are many samples that are relatively similar to each other, whereas the false positives in our heuristic are mainly random content. So again, we could use a fully automated approach to improve our results, and we can do an outlier elimination via density-based clustering to get a very high precision and recall. And this is the results of the density-based clustering. So as we can see, we see several exploit kit campaigns, such as from Blackhole, an updated version, a fake Flash player campaign, some false positives, and many fake antiviruses campaigns. And as we can see, the vast majority of benign web pages were discarded as noise. Also, there were some, obviously some scams discarded as noise. And I should also mention that, as you can see, some of the campaigns appear in multiple clusters, and this is due to the fact that we observed that several minor variations or even bugged samples in the campaigns. So even though they, at a human overlook, they are actually from the same campaign, and there's minor variations, they actually tend to be split as different clusters. So there's an example of what we actually found to be obfuscated. Sometimes we saw, as expected, the fraudulent content or the domain names of the next page that the exploit is redirecting to. There are a couple of examples that we found also in benign web pages, and we had to whitelist, and then still are in some cases a source of false positives, so benign pages that are detected. One is very expected, the obfuscation of email addresses. And this is a relatively common practice. When you have an email address in the page, you might want to encode it so that the bots that scan, that crawl the web to harvest email addresses for spamming purposes do not immediately catch it. So this is a relatively expected result. A less expected result was that we observed that there are several cases of links being obfuscated. And our intuition on this is that this is most likely done for search engine optimization purposes. In fact, Google has, at the time, had recently de-emphasized the nofollow attribute. So you cannot completely exclude pages on your website that you link from getting some reputation in your website. And apparently some web authors do not completely trust Google to make the right decisions in what pages they index and they do not. So for instance, they might try to hide the link to their, for instance, their contact page or their login web page. They might try to exclude it completely from Google even seeing them. And this is a relatively unexpected result, but again, done even by benign authors. Now, moving to our second heuristic, we built a heuristic that tries to get counterfeit certification seals. So what is a certification seal? So certification seals are these small images like this one, this couple that we have here, and that are meant to certify that there was a third party that has somehow reviewed the website and is certifying that the website respects some kind of property. There is no real standard on what the seals are supposed to mean. Just to give a few examples, some are done to certify that the data is transferred securely, some that relate to the business practices of the owner of the website, and so, or that the site is free from malware, for instance, and so on and so forth. But in all cases, these seals, whether they are legitimate or not, are included to make visitors more comfortable in browsing the website and presumably more likely to spend time or money on the website. And unfortunately, as there is no standard on the meaning of the seal, there's also no standard on how the seal is to be included or how the seal is to be verified. How do you verify that, McAfee has really scanned the website, or that, Symantec is really vouching for the website? And unfortunately, the browser cannot help the user here. These are not, there's no HTTPS protocol here. These are just images included in the page. And in fact, they are quite complicated to check even for an expert user. Even though all the data is available to a program that scans the web page, it's not that trivial to build an automated program that does that, because the correct way to do this, in principle, is to scan the terms of use for each seal and see exactly how it is mandated to be included. For instance, many seals are to be included via JavaScript, for instance, and are supposed to be verifiable by clicking on them. But again, this is not easily enforced. And as a result, this is extremely easy to counterfeit. If you want to counterfeit a seal, well, more or less what you have to do is just make a little image that looks like a seal. Maybe you make it up completely, such as saying that the FDA has approved you, or you can alter existing logos, or you can even put in an exact copy of the logo that as it exists. And as I mentioned, you're supposed to click on the seal to get a verification page, but as you fake the seal, you can also fake the certification page. So when you click on check license, nothing prevents you from making a fake license page come up. So again, this is not something that is easily detectable by a user that is not familiar with how the seals are supposed to be used and included. So again, we created a heuristic to detect this. We created a very simple heuristic. This is, again, fully automated. In particular, we looked for common images that have sizes that are comparable to the seals. We OCR and look for words like secured or approved that are kind of likely to appear in seals. And when we are presented with an unknown page, we try to find seals in there by finding the similar images from the ones that we know. And we consider the page fake if they do not link to an off-site certification page like a regular seal would normally do. So again, this is a very simple heuristic. But then again, this particular type of scam is really targeting humans, not really the program. The program can use this very simple heuristic to check if the seal is a likely benign or likely malicious case. And in fact, this very simple heuristic correctly flagged about 400 rogue pharmacy samples with 0 false positives. And as a matter of fact, this, as we will see later, this proved to be a very valuable starting point for detecting this entire category of scams. So where are we now? We have 2 heuristics that are with relatively good performance detecting malicious web pages, but obviously they are not complete. But there are a few interesting things there. For instance, one is that they tend to find pure scams, so scams that are not really targeting a specific browser or a specific OS vulnerability. These heuristics tend to detect scams that succeed via deception of the user, not really via mechanical obfuscation, so to speak, or mechanical exploitation. So we wondered, these heuristics are pointing out the code, the stuff that the original author somehow wanted to hide or deceive with. And then we wondered, could we use them to detect more? Could we use, for instance, the few fake antiviruses or pharmacy scam pages that we found to detect more? Instead, in essence, we are asking, are these heuristics pointing in the right direction, so to speak? And to answer this question, we built a very simple proof of concept general detector, so a detector that starts just from our 2 heuristics, so nothing complicated as far as initially finding the malicious web pages. And then it tries to detect if an arbitrary page is malicious or not. And its construction is relatively standard. Again, more details are on the paper, but essentially what we do is try to find contiguous regions of text that are common in each of the classes that we found or in the counterfeit certification seal pages. And we try to emphasize obfuscated word. And then we consider flag malicious if there is a region of the text of the page that is close to the ones that we already know. And this is an example signature for a fake antivirus campaign, like initializing virus protection system, initializing threat with the original misspelling made by the malware authors, initializing threat protection system, and so on and so forth. And these are the final results of our proof of concept detector on those 50,000 random URLs from WebOet with no extra filtering. And as we can see, there was a significant increase on the number of pages that we detected, number of true positives and raised significantly, and as we can see, we still have a very good precision and a relatively good recall. So what we can conclude is that this heuristic did indeed generalize quite well. As an example, we found several pharmacy scams from even different campaigns that were not originally detected by our main heuristics. But we also had some false negatives and obviously some specifically samples that were very different from the original pages that we detected. This is relatively expected from any signature-based system. So to conclude, we think that these heuristics are not enough, obviously, to create a complete security system, but this view difference can, in our opinion, be a very useful addition to many analyzers and is especially well suited to complement exploit-based detectors because it does not tend to detect the exploit-based vulnerability, exploit-based scams, but instead it tends to detect human-based scams. And in particular, there is what we think is a good property of this type of heuristic is that, in a sense, they present the fraudsters with a relatively difficult choice because they can, well, one thing that they can do is they can exploit this difference. So they hide from the program or from the user, but then again, this type of heuristic can detect them, and in our case, even expose other similar scams that we have seen for the rogue pharmacies. Or the other choice that they have is to present exactly the same information to the human and the program, but then again, this would escape our heuristic, but it would facilitate signature construction. So we think that this is a relatively good property to have for a system. And on this note, I conclude my presentation. So thank you for your attention, and I'm happy to accept questions.
Thank you. I was wondering, so you said you had found a couple of, so I have two questions. You said you had 0 false negative. So does that mean that you had, on all the pages that had obfuscation, you hadn't missed any of them? Or does it mean that all the malicious page you had, you also found them because they also, each of them had obfuscation? I guess this is the former, not the latter, right?
So this is relatively only to whether the content was obfuscated or not.
Okay.
So independently of whether the page was malicious or not. Okay. So just to do an example, like a false negative here would be a page that actually had obfuscation, but our heuristic did not detect that.
Right. And so for the 56 benign, so that means in 56 cases, on good pages, there were some sort of obfuscations, right?
Yes.
So can you elaborate a bit on that and tell us what the risks are that this practice, which apparently is already taking place, could become generalized and therefore makes this approach not work anymore? So in other words, why do they use obfuscation and what's the risk and others do it also?
Yes, I understand. So this is really up to the web author, whether he wants to do it or not. Like, just to make an example of a couple of benign pages that were using obfuscation. For instance, let's say you do a tabbed web page that you have like several tabs that you can click on to select different parts of the page. And let's say that you transfer each of these tabs from doing an address request from your database, okay? For instance, an example that I remember off the top of my head is that this author was transferring this completely benign content in a base 64 encoded version and decoding it on the fly in the web page. So this author was not really trying to hide his content. He was just doing it presumably because maybe he already had the page base 64 encoded in his own database. So to answer your question, we did not verify any, we did not see in our dataset any particularly common usage of benign obfuscation, with the exception, as I mentioned, of obfuscation of email addresses and obfuscation of links. And these we specifically whitelisted. But again, a full answer to this question would only be, is in a sense, in the hands of the web authors. Of course, I mean, you could say that web authors could start using obfuscation benignly, but this is not what we saw in our data set. That's it.
So for the detection of the fake seal detection, you kind of achieved very high precision. And I wonder if you have thought about kind of applying these sort of techniques to do it in an online way, so that actually as users browse, you can give direct feedback about possible fake seals.
So this is potentially doable. We opted for a very simple, fully automated approach. As a matter of fact, I think that the best approach, if one wanted to do it in browser, would be to have some sort of standard on how the seals are supposed to be included, so that the browser had the information right there to verify it. And as a matter of fact, even if one wanted to do heuristically, a possible alternative that we considered was that there are relatively few legitimate issuers of seals. Like, there are really just a few, like Symantec, McAfee, GeoTrust, a couple of others. So in principle, one could go and review the terms of services for all these legitimate issuers, and could potentially build in the browser a verifier for these seals. So this is, again, a very possible approach.
Just a curiosity. So is that a feature that now will be added to WebAwet? Since you are kind of close to the WebAwet authors, or maybe only in the commercial version, I don't know.
So this is more of a question for the WebAwet maintainers than for me.
Oh,
but,
yeah,
I mean, we will consider.
Probably not. Not at the moment.
Exactly. It is not immediately planned to be included in WebAwet, but yes, in principle, it could be included if necessary.
Thanks.
Okay. If there are no further questions, let's have the speaker again.